In this video, I'm going to be working some problems around about the definition of a subspace in linear algebra. And this is going to be linear algebra homework 4.1. All right, so the first set of problems is just sketch vectors, right? And so the first one is u and negative u, and that's obviously going to be pretty easy because you use a two-dimensional vector. And so I'm going to just say number 1, just draw R2. Maybe I'll use the color for u. U is x is 3 and y is 1. So that's going to be u right there. And then I'll draw negative u in red. It's going to be the same, but in the opposite direction. And what I'll tell you while I'm drawing this is that kind of the idea here with these is that in the plane, vectors that are proportional, that are just, u 2v and u plus 2v, well, u or say v and 2v, they're going to lie on the same line. U and negative u are going to lie on the same line. If we're plotting them, all emanating from the origin, then they're going to lie on the same line that runs through the origin. But we'll look at that. So number 2, u, v, and u plus 2v. So, all right. Well, let's just think about what 2v is going to be. It's going to be 4, 2, so I need a little more x-axis. And wait a second, u plus 2v is going to be, that's going to be a lot of first quadrant. So maybe I will try that again and just draw that. Yeah, that'll be better. I should have been a little more strategic there. All right, so u is 3, 1. Let's see, for u blue last time. Let's see. V, or 2v is going to be 2, 4. Let's try it also in blue. So that's 2v. And then u plus 2v, there's a number of ways of looking at it. You could slide this thing over here so that the bottom of this sat at the end of that, and that would give you some point over here. You could make a parallelogram out of them, and then the diagonal of the parallelogram is going to be the sum of u and 2v. Regardless, it's going to be 3 and 2 is 5, and 1 and 4 also 5, and so the sum is going to go about to here. Oh, oops, I was supposed to label that. U plus 2v. And that's, okay, if we take 2 and we add them together, their sum will lie on the plane defined by the first 2. And the third one is x, y, and x minus y. Let's see, I might need a new scrap for that because this is a 3-dimensional situation. I can't remember. Hold on. Yeah, for a second I thought because I was seeing a lot of positive values in x, y, and z, or the 3 components of vector x and vector y, that might be a little confusing to call it x, y, and z. But because I was seeing a lot of positive numbers, I thought I might have wanted to draw it from the front perspective where everything we're looking at, kind of the positive axes. But I've decided that I think this will be the way to go. So x is going to be where the first coordinate is 0, the second coordinate is 1. Maybe we'll mark that there. And the z coordinate, the third coordinate, is 3. Okay. So what we're going to do is just kind of trace out parallel to that. We're above that 1. I think that's going to be x. And I will draw x in blue. Then y is going to be 2, 1, 0. So I need to mark off 2 on the x-axis, which I don't know, looks like it might be about right there. 1 in the y direction, we already have that marked, and 0 in the z direction means it's going to be sitting in that plane just right there. It's, yeah, you can just pretend it looks right. And I'll draw this one in red. That's y. And if we subtract them, then x minus y is going to be that. It's going to be the one that goes from here to there. And although you could certainly draw it from the origin, you know, it wouldn't, I don't think it would carry as much meaning. I'm going to get another color. And I'm going to just connect these. So x minus y is going to be hold on. Yeah, definitely this one. I'll call it x minus y. Okay, and the idea here is that if we take 2 and we add them or subtract them, the third is going to lie on the same plane defined by the first 2. You can even see that triangle that's part of the plane. Okay, that's the first thing. Sketch W, which is a subset of R2, and determine if it is a subspace of R2. All right. Now, to determine if it's a subspace, it's going to have to meet all 3 of the requirements, but to determine if it's not a subspace, we're going to just disprove one of the requirements. So it might be a good idea for me to go over here to the side and remind you of the definition of a subspace. So there's the definition of subspace. Remember that it needs to contain the 0 vector, be closed under addition, and closed under scalar multiplication. Okay, so let's number 4. It's the set of all x1 and x2 such that x1 plus x2 equals 1. Okay, in the y equals f of x world, that's y equals 1 minus x. So I'm going to draw a picture of R2, so this will be variable x1, and that's variable x2, and the subspace or the subset is that line. Okay, I'm proposing that it is not a subspace. Okay, so this is W. Not a subspace, and the reason I would give is because 0 is not in W, it does not pass through the origin. You could go and see that this space is not closed under addition, right? The vector 0, 1 is on the line. The vector, pardon me, that was 1, 0. This is 0, 1. If we added them together, we'd get 1, 1. And that would be up here. That would not be on the line. Also, 1, 1 is not a pair of x1 and x2 that add to 1. So not closed under addition. Not closed under scalar multiplication either, right? Because if I took 0, 1 and multiplied it by 3, I'd be up here, no longer on the line, right? So this one, not a subspace. This is number 4. And number 5, x1 equals negative 3x2. So x equals negative 3y. So y is negative 1/3 of x. Negative 1/3 of x. Pardon me. That's W. All right. I think this is going to be a subspace. So I need to show that the 0 vector is in W. Okay. 0 vector. Yes. 0 equals negative 3 times 0. Okay, that's good. So addition. So let A be, negative 3a2 and a2 plus B be negative 3b2 and b2. If I add those together, I'm going to get negative 3a2 minus 3b2, which is something I could factor a negative 3 out of. So a2 plus b2. Still in a shot, plenty of room. And then down below, I have a2 plus b2. And if you look at that, that's a situation where the top component is negative 3 times the bottom component. There you go. It fits the specification, so it is closed under addition. And I don't really have enough. Well, I guess I have enough room to put a check mark there. Now, scalar multiplication. Let's multiply A. Oh my goodness, that's a big mosquito. I'm not sure if you saw that. It was just massive, and I'm going to kill it. But okay, anyway, negative 3a2 and a2. this is negative 3ka2 and ka2, right? But if I kind of use the associative property of multiplication of real numbers, I could say, oh wait, hey look, the first component is negative 3 times the second component, still in W, okay? So this is a subspace. All right. Number 6. It's the set of all multiples of 1, 3. Okay, let's look at that. This is R2 and number 6. Okay, so 1, 3 is there, and it's all possible multiples. So that's like all of the, less than 1 multiples. Here are the larger than 1 multiples, and here are the negative multiples. Okay, so it's a line passing through the origin, pretty good chance to be a subspace. It's going to be a subspace. And so I can say, all right, look, W contains the 0 vector where t equals 0, right? Addition. Let A be, some number A times 1 and 3, just, any real number A. Plus B would be B times 1, 3, so B and 3B. So this would be A plus B, and this would be 3A plus 3B, which is the type of thing I can factor a 3 out of. And again, look, this is A plus B times the vector 1, 3. Okay, so T equals A plus B, and we're still in W. Okay, for scalar multiplication, if I took K times A and 3A, that would be Ka and 3 times Ka, again, using the associative property of multiplication of real numbers, and then I'm determining, yes, all 3 conditions are met, W is indeed a subspace. I'm going to take away the definition of subspace. I think it's been up there long enough, and I think you know what it is. So, number 7. W is going to be, the set of all x where the first coordinate is positive and the second and third coordinates are 0. Okay, that's interesting. I think that's just going to be the x-axis. So maybe I can just highlight this set for you. Oh no, I've got actually something better. All right, that's part of 3-dimensional space. And then W, the thing that we're interested in talking about right now, is going to be this red line. Okay, so this is a ray that goes through the origin, or that starts from the origin. The question is that going to be a subspace? And, well, first of all, it's not, because the 0 vector is not in it. But suppose that I had made this a greater than or equal to 0, so that that wasn't the one that broke, right? And then maybe I'll kind of fix that by putting a little red dot there to indicate that it is there at the origin as well. Okay, if that's the case, then the 0 vector will be in the space, so that won't be the reason it's not a subspace, but scalar multiplication will be the reason. Okay, this is closed under addition. If you take any of these two with positive numbers and add them together, it's still going to be in that space because positive plus positive equals positive, and 0 plus 0 equals 0. But it's scalar multiplication that's the trouble here. So if you take, let A be a positive number. If I take negative 2 times A 0, 0 equals negative 2A 0, 0. Okay, because A is a positive number, I know negative 2 times A has to be a negative number. This is not in W. Negative 2 is a real number. Okay, so this is not closed under scalar multiplication, so W is not a subspace. All right. Number 8. What is this one? All right, this is the one where all 3 of them add together to equal 0. This is This one's going to be tough to draw because I know, because I tried to draw it in class and it didn't really go that well. So I had an idea. Oh yeah, I think I'm going to draw you a kind of a side view of this. All right, this is basically it's the plane x plus y plus z equals 0, but that it runs through the origin. Okay, well, now that's a good sign. As for drawing a picture of it, what I'm going to do is I'm going to draw x. I mean, it could be y, just the same, versus z versus x. And this is a side view of the plane. So like, you know, this is the y-axis coming right at you and then going away. You can't see it at all because there's no depth, and I just lined it up just that way. W is going to be pretty sure it's going to be that plane. Okay. So maybe I'll give it, you know, a little bit of depth. Down that y-axis. And maybe I will be able to try and, I don't know if that's a good idea, but you know, I did. It's kind of coming down through the, no, that didn't really give it. That's not a very good drawing. It's the best I could do. Okay. This is one that if you plotted it on a three-dimensional plotter, you'd be wanting to like rotate around, and I don't have that ability to draw something that rotates. Okay, so regardless, I'm going to show you that this is a subspace because it meets all the requirements, and I'm just going to check all of those algebraically on the specification you've got right there. All right, so we're going to say, is the 0 vector in W? Yes. That's x1, x2, x3, all of the xi's is equal to 0. Addition. Okay, a1, a2, a3 plus b1, b2, b3 with, you know, the sum of the a's equaling 0 and the sum of the b's equaling 0. Okay, and you may get to this point and you may be like, hey, what am I supposed to do here? Right? Like, how do I show this? And remember that it's the set of all vectors where if I take the components and I add them all together, it needs to equal 0. So let's add all these components together. And see what happens. Well, what's something I could rearrange the way they're written, right? Because 2 plus 3 is the same as 3 plus 2. So I'm going to call it a1 plus a2 plus a3 plus b1 plus b2 plus b3. And because a and b were in the space originally, these things added to 0 and these things added to 0 as well. So I've got 0 plus 0 necessarily, and that's 0, so I'm still in the space. All right, and for the same reason, it's going to work out on the scalar multiplication. So I'm going to call it, okay, on times, it's going to be, let's multiply k by a1, a2, a3, and that's going to be k a1, k a2, and k a3. If I add all the components here together, I can factor. If a is in the space to begin with, then their sum is 0, so that's equal to k times 0, and that's equal to 0, which means that I'm still in the space. Okay, so it is closed under scalar multiplication. Conclude that this is a subspace. All right. 9. W is the set of all A, B, and C where the sum of their squares is 1 and C is greater than or equal to 0. Okay. This is part of the equation of a sphere, which I don't think is something we've talked about. You know, this is linear algebra, so it's not a good Not a good chance. I actually think I want to, well, I'll change it in a second. So what I'm going to do, I'm going to actually start with the half sphere, I think. Okay. And c is greater than or equal to 0, so it's going to go all the way down to the xy plane here, where z equals 0. That's what I'm going to do. I'm going to let me think. Probably don't want to draw it like that. Yeah, there it is. All right, so that's pretty decent. You can envision that being a sphere, especially if I were to kind of draw in the axis and the other side. That's pretty decent, especially for my skills. Oh, and of course we're going to need a z-axis. Yeah. All right. That's half of a sphere. That's as good as I can draw. So it's just the shell, though, because it's the set of all points where a squared plus b squared plus c squared equals 1. So the 0 vector is not in there. So what I want to say, I'm going to change this to be less than or equal to 1, so that the 0 vector is in, and I'm not just going to have like a easy way out and say, oh, 0's not in there. Okay, so if it's less than or equal to 1, then it's all the points on the inside and on the shell, right? It's like, it's solid. And so I can go over here and I can say, all right, what am I going to do? I'm going to say, well, the 0 vector's in it, but I think it's not going to be closed under scalar multiplication, because if I took, you know, this point here and added it to that point here, okay, so this is 0, 0, 1. This is 1, 0, 0. If I added them together, I'd have 1, 0, 1. And that does not fit it, because 1 squared plus 0 squared plus 1 squared is not less than or equal to 1. Okay, so whoops, no, whatever. It's not in W, so this is not a subspace. All right. Give a set theoretic description of the points as a subset of R2 and determine if it's a subspace. Well, who knows, maybe we can do that. The points on the line x minus 2y equals 1. I know that that's going to have slope 1/2, and it's going to have x-intercept of 1 and y-intercept of -1/2. Whoops. I should definitely have drawn the line first and the intercept second, but, you know, I know that. Should have known that, but you live and learn. All right, this does not go through the origin. 0 is not in this, so, you know, not a subspace. Oh, we were not supposed to draw a picture. We were supposed to give a set theoretic description. Okay, whoops. Okay. W equals the set of all x in R2 for which x1 minus 2x2 equals 1. Okay. I should have put in R2 like we did up there, but, you know, I think it's implied. If it's a line and it only has x and y, it's in R2. That's number 10. Number 11, the points on the x-axis. Oh, and yes, this is not a subspace because it does not contain the 0 vector. 0 minus 0 is not equal to 1, not a subspace. Okay. Let's see. I can shift this over here, yeah. I'll just start working. All right, the points on the x-axis. That's this W is the set of all. Oh, and it's implied to be R2 up here. I didn't read that, I guess. Okay, so the points on the x-axis. W is the set of all vectors for which, well, on the x-axis, the y-coordinate is 0. So it's x2 equals 0. It's the line y equals 0. That's another way. Yes, this is a subspace because, okay, 0 vector, yes, 0, 0 has second coordinate 0. If we add 2 together, like a0 and b0, we get back something with a 0 coordinate, right? 0 second coordinate. A plus b and 0. And if we have, what was I thinking? Oh, scalar multiplication, k times a0, it's, you know, ka times k0, and k0 is always 0, so it's going to still be in. So yes, fits all the specifications. Number 12 is the points on the upper half plane. All right, by the upper half plane, they just mean greater than or equal to 0. So W equals the set of all vectors in R2 for which the second coordinate is greater than or equal to 0. No negative y's. But we kind of already saw something like that up above when we had that array where, you know, as a number A was greater than or equal to 0. That is, and that was not a subspace, and this is not going to be either because this is very much, you know, the similar idea. It's like cutting the space in half. It's not infinite anymore. It's not as infinite, right? And so what's going to happen is it's going to break on scalar multiplication. So if we had, you know, like, you know, let x2 be greater than or equal to 0. If we had negative 1 times, you know, x1 and x2 with x2 being greater than or equal to 0, that's negative x2, which has got to be less than or equal to 0. And, you know, provided, you know, maybe let this be greater than 0. Then that will be less than 0, and I will no longer be in the upper half plane. And we don't really care anything about x1, right? No specification on that. This is not a subspace because that's not in W anymore. It's not enclosed under scalar multiplication. The points on the parabola y equals x squared. This is, whoops, way too far. There it is. All right, let's go below here. And y equals x squared. So W is the set of all vectors x for which x2 equals x1 squared. Y equals x squared. Okay, the 0 vector is on that, but it's not going to be closed under scalar multiplication because if we have, a and a squared plus b and b squared, we're going to get a plus b and a squared plus b squared. And I know y'all know that a squared plus b squared is not the same as taking a plus b and squaring it, right? There's be that 2ab term. Okay, so this is like unless a and b are both 0, that's not going to work out. Or maybe one of a or b. I have to think about that. It's not worth it because this is not in W, so I'm going to conclude it is not a subspace. Okay. Not closed under scalar multiplication. Now, the last set give a set theoretic description. The given points is a subset of R3 and determine if W is a subspace. Okay. Okay, it's a plane. It contains the 0 vector. Yes. Okay, so that's kind of what you're going to find is that line through the origin, plane through the origin, automatic subspace. And so x plus y plus 2z equals 0. This is the set of all x in R3 for which x1 plus x2 minus 2x3 equals 0. And I'm going to just say yes, it is a subspace in the interest of time. So the points on the line with parametric equations x equals 2t, y equals negative 3t, and z equals t. Okay, we could say, you know, x equals 2t, negative 3t, and t, where t is a real number, or we could factor out the t and say it's all multiples of 2, negative 3, and 1, which is kind of a direction we're going to head in this course eventually. And I could write it like that. This is a line with t equals 0. It goes to the origin. So a line through the origin, yes, it's going to be a subspace. Whoops, forgot to write that. The points in the YZ plane. Okay, the YZ plane is the, maybe I'll draw it for you. X y, z. So on the yz plane, that's where x equals 0. I think that drawing shows you why. And so it's the set of all x in R3 such that the first coordinate is equal to 0. Okay, I would just draw your attention back to the one where it was the set of all points on the x-axis earlier. It's going to work the exact same way, determining that this is a subspace, but it's a plane that goes to the origin, so that's going to be a yes also. And the points on the plane y equals 2. Okay, w is equal to, push this down to the side a little bit, it's where it's y equals 2. So, wait, was it y equals 2 or z equals 2? Y equals 2, okay, that's a little, actually I think that should be all right to draw. I'm going to let 2 be ways out here. And so, you know, the plane y equals 2 is going to look right. We can see that we definitely cannot. It's blocking the axis around there. It's a very rudimentary sketch. Yeah, could have done better, but it'll work for now. I mean, you can see it's not going through the origin, so it's not going to work. But it's just the set of all x in R3 where, what is it, you know, x2 equals 2, y equals 2. And I think this one is going to be closed under addition and scalar multiplication. No, not scalar multiplication. Because you multiply the 2 by some number, and it's going to have a different y coordinate. Yeah, and it won't be closed under addition either. Pardon me. I was just thinking completely wrong. So I'm going to conclude that no, not a subspace. Okay. That's all I got for you for this video.